welcome to PhysChem with Liz. I'm Liz, and in today's short video, this is the second one in the basics of NMR, and we're going to look at something called chemical equivalency. So we're going to define what chemical equivalency means. You don't have to learn a worded definition for this one. And we're going to practice identifying the number of hydrogen environments by looking at molecules, and also by doing it the other way and looking at NMR spectra. So first of all, we can have something called chemically equivalent protons in molecules, and what that means is that these protons are in the same environment as each other. So what I've drawn here are three different molecules and three different spectra. Now, I'm going to demonstrate this concept of chemical equivalency by labelling the different kinds of proton environments, or equivalent protons, same thing, and then from that we're going to match them up with their spectra. Now you don't need to know about splitting for this, we'll do that in the next video. Just the number of different kinds of proton environments will match with the number of signals in the spectra. So this first molecule we've got here, this is ethanol. Now, we've got three protons bonded to this carbon, and we say they're chemically equivalent. What that means is they're in the same chemical environment, so they're bonded to this same carbon, and they all have the same neighbour, this carbon. So this is one proton environment. So let's call it HA or H1. Then over here, we've got two protons bonded to this carbon. And these are equivalent to each other. That's another proton environment. Let's call it HB. Because they're both connected to this carbon and they both have the same neighbours. But can you see that these are different to each other because they have different neighbours? And lastly, we've got this alcohol hydrogen on the end. Now this is in proton environment all by itself, because as you can see, there's only this proton that's directly bonded to this oxygen. So that is different to these ones as well. So we'll call that HC. Now, we've got three different kinds of proton environment. That means this has to match up with a spectrum with three lots of signals. So this molecule of ethanol matches with this spectrum here. So something to mention, I think I did mention it in a previous video on chemical shift, I'll mention it again. Even though we've got splitting, so this signal is split into four, it's called a quartet, this still counts as one signal. Okay, if it's grouped together, even if it's split, it's one signal in proton NMR. So 1, 2, 3 signals altogether from the three different proton environments. Then over here, we've got a representation of benzene. You recognise this if you're studying A2 chemistry and you've done the aromatic module. If you've not, don't worry about it. You might get asked to identify equivalent protons on molecules that you're unfamiliar with. If you do, you just apply the same rules. So each proton on this molecule is attached to a carbon which is next to another carbon. On one side we've got a single bond, on the other side we've got a double bond. And that is the same for all of them. Therefore, all these protons are equivalent to each other. So we've only got one kind of proton environment here. Therefore, this molecule is responsible for this signal on this spectrum. So to save space, I've only included the part of the spectrum where the peak is. And if you've watched the previous video on chemical shift, you'll know that the position of the peak tells you the kind of proton responsible. So between 7 and 8, this is due to aromatic protons, like benzene. And then here, with the alcohols, that's a tricky one. I should have picked a different one. That can actually appear anywhere. But we can figure out which signal that is from the splitting, which we will look at later. So finally over here, we've got a symmetrical molecule. It's called diethyl ether. Now, if you have symmetry, this reduces the number of different proton environments that you have because of that symmetry. So this molecule is symmetrical down the middle where the oxygen is. So these 3 protons here are chemically equivalent to these 3 protons on the end over here. And that is because on one side they have no neighbours, on one side they're next to a CH2. That's the same for both of them. So they're in the same environment. Then we've got CH2 protons, and these are chemically equivalent to each other because on one side they've got a CH3 as a neighbour, on the other side they have an oxygen as a neighbour. But they're different, the CH3 protons, because they have different neighbours. So HA, HB. This matches with this spectrum because we've got 2 types of proton environment, 2 lots of signals. So that was just a quick summary tutorial on chemical equivalency or types of proton environments. I hope that was helpful. If it was, please like and subscribe. And any questions, comment below or email my Gmail. Thank you. See you again.